Hey folks, wanted to spend a little bit of time going over some of the graphs that you're going to be seeing. We've already talked about a position versus time, velocity versus time, and acceleration versus time graphs, but today I wanted to focus on potential energy versus time and kinetic energy versus time, and then also potential and kinetic energy versus position graphs. You're going to have to know how to sketch all of those. First of all, I've got this thing set, I think, at negative 4 meters per second. I'm going to go ahead and click on this and make me go away. Let's verify here. So I've got a velocity of negative 4. So that means we're at the midpoint. The spring is unstrained right now, and the object will be moving to the left. Since we're at the midpoint, we should think about our position graph. That means our position graph is also going to start at the midpoint, and since we're initially going to the left, that means the position graph should be heading towards the negative axis, which means this should be a sine graph or a negative sine graph when we hit play. All right, so as we make this oscillate through a little bit more than one cycle, you will notice that this is a negative sine graph and it has a period of about 2.81 seconds. Okay. Over here, this is the energy stored in the spring versus time. Notice that there is no negatives on this graph, and it should make sense. The equation is 1 half kx squared, so we're not going to get a negative value. But this corresponds to, at the greatest position of negative 1.8-ish meters, we have our greatest energy stored in the spring of about 6.4 joules, it looks like. Yes, the maximum value is 6.4 joules. Okay, so we'll remember this when we come back to another graph here in a little bit. Let's back this up. So based on what we know so far, since our position graph is a negative sine graph, let's switch this over to velocity. Since the position graph is a negative sine graph, we would expect now that the velocity versus time graph is going to be a negative cosine graph. So let's verify that through one cycle. And there it is. So we end up with a negative cosine graph, and our maximum velocity is negative 4 meters per second. And then it oscillates up to positive 4 meters per second and then comes back. All right, last one of these before we get moving on. Let's go ahead and verify our acceleration versus time graph. So now with the acceleration versus time, we should expect, since it's at the midpoint and the spring is relaxed, there's no force from the spring, so there won't be any acceleration. As it begins moving to the left, the spring force is restorative, so the spring is going to want to push it back to the right. So our acceleration graph should be going up from the midpoint and be a sine wave. So let's verify that, and there is about one cycle, and it gives our maximum and minimum accelerations. Okay, all right, next thing. I'm going to switch this over to a linear kinetic energy versus time graph. So remember earlier we said we had about 6.4 joules of potential energy when the spring is fully compressed at the amplitudes, and the graph did not have any negative values, it's just all positive. As we go through about one cycle here on the kinetic energy versus time graph, so we are about exactly one cycle here. Notice that the kinetic energy versus time graph is just completely opposite from the potential energy versus time, where the maximum kinetic energy at the midpoint is 6.4 joules, and at the midpoint we have 0 joules of spring energy. So it makes sense. I could go through either of these graphs at a specific time interval, find the kinetic energy and the potential energy and add them up, and it should equal 6.4 no matter what, no matter where I measure it. Because remember, we're talking about an ideal spring here, and an ideal spring is always going to restore it back to its equilibrium position. Okay, last graph I want to talk about. You guys will see this a couple of times, so I wanted to make sure. And I can't do it with the spring, but, oh, wrong one. I can do it with the kinetic energy versus time graph. Let's switch the kinetic energy versus time graph to a kinetic energy versus position X. So what's going to happen here is we're at the midpoint, so we should expect that the kinetic energy graph is going to start in the middle I'm going to slow this down just a little bit so we can watch a full oscillation. And there it is. The kinetic energy graph starts in the middle, but now that we got back to the midpoint, notice the graph just went down to 0 and then came right back up. And now we would expect that the graph would complete its cycle as it goes back through. So notice that the kinetic energy versus position graph just simply oscillates back and forth between the two positions, and the graph is just totally positive, where at the midpoint it is 6.4 joules, which should make sense. If I could change this over to a potential energy versus position graph, it would just be completely the opposite. It would start here, it would oscillate down through and come back up. Okay, actually it would have started in the midpoint and then gone here and back up, but you get the picture. But same thing, any 2 points that I add up on the potential energy and the kinetic energy versus time or versus position graphs will always add up to be 6.4, because that is the total energy of the mass spring system, and that energy remains constant. Okay, that's all I've got for today for you guys. Next video will be on next topic when we get to pendulum motions, and then we are done with the first half of the unit.